Section 1.2, we're looking at constructing models to solve problems. In particular, we're going to see a number of formulas in this section. A formula is an equation involving two or more variables. And a function is a rule for determining the value of one variable from the values of the other variables given. There are some common formulas that I'm going to kind of throw up here. Simple interest. So simple interest is what happens if you were to put your money in the bank and they calculated the interest one time. That's simple interest. Perimeter of a rectangle is 2L plus 2W, right? Finding the distance around of a rectangle. Distance equals rate times time. It looks like dirt. That's what it looks like. People remember it that way sometimes. Temperature, right, converting between Celsius and Fahrenheit. You don't really need two formulas. There are two formulas, one written as Celsius equals, the other one written as Fahrenheit equals. But as long as you have one of them, you can always solve for the other variable. So temperature is that one given in Celsius. Sales tax. Sales tax always confuses people, yet you guys do it every single day. You don't really pay attention to it sometimes, I know. But sales tax is the price of the product plus the tax rate times the price of the product. So if you go and you buy pizza, right? If you buy pizza, there's the price of the pizza and then whatever the tax rate is. And so in Shawnee, it's 9 point something, I'm pretty sure. And so they take that as a percentage, right? 0.095, let's say, and then times your price of your pizza, and that's your tax. So the RP at the end is the tax on the pizza, and the P is the price on the pizza. And add those together, and you get the actual price you pay for the pizza. Another one for a rectangle, area of a rectangle is length times width. And then work actually looks a lot like the distance formula. Work equals rate times time, just like distance equals rate times time. It's the context that changes, of course, to give you those different quantities. I don't need you to memorize any of these specific formulas. I'm going to give them to you on your test. I will not tell you, this is the formula for sales tax. This is the formula for work. All you'll be given is the formulas on the right-hand side, and you need to know what they're for. So it is worth your time to make sure that you know which one goes with which. I don't know if you want to do that as a matching game with note cards or whatever, but or just have a list of them and be able to identify them. But that's something you need to be able to do, all right? So that when you get to the test, you can utilize what I'm giving you to the best of your ability. So we're going to spend the rest of the time pretty much today working some examples. I have one more component where we're going to be looking at some problem-solving stuff. But the first couple of examples, first three in fact, are actually taking an equation and simply rewriting it for another variable. So we're not going to find a quantity value, like a numerical value for each of our answers here. We're going to find a formula in another sense. So I mentioned it over here on the temperature, right, that Celsius is equal to this expression with Fahrenheit in it. Well, you can rewrite that and get a formula that says Fahrenheit equals with Celsius on the right-hand side and some other symbols and numbers around it. That's really what we're doing for the first three examples. We're taking an example that we're given and we're rewriting it for a different variable. So on the first one, we want to solve this for B. So we're trying to move everything that's that's connected to B to be not connected to B, to move to the other side of the formula. So one of the things to take care of real quickly is that 1/2. It's very tempting to say, well, I'll divide by 1/2, but as we've encountered back in Chapter P, dividing by fractions means multiplying by the reciprocal. So it's a little bit cleaner for us to simply multiply by the reciprocal, so we would have 2A equals BH. Do you guys know what this is originally the formula for? It's the area of a triangle, okay? I'm not asking you to know it, I'm just curious if you did. It's the area of a triangle. And then what would I do finally to solve this for B? Yeah, I divide by H. I tend to rewrite my equations at the end with the letter I'm solving for isolated on the left. You can isolate on the right, it doesn't matter. But this is 2A over H. So that's all this question is asking, is to rewrite the equation solved for B. Part B, that one you may or may not recognize that equation. That's the standard equation of a line. We don't see lines written that way very often, but it is what it's called. And so we're going to take this equation and we're going to solve for x. So whenever we're solving for any variable, we're moving from the outside in. It's kind of like opposite of order of operations when you're trying to solve something. but we're working from the outside in. And so we're taking what's furthest away from x, which in this case would be the the by over here, and we're going to shift it to the other side. Since it's added, we will subtract. So I've got ax equals c minus by. Or you could put negative by plus c. And then what would I need to do to solve for x? Divide by a. So x is equal to c minus by over a. Any questions on that one? The next one is by far the most challenging to solve for. This is an equation that talks about rates. So you probably have not encountered this, at least not written in this formula perspective before. Our goal is to solve for R2, and the thing that makes this tricky is that R2 is in the denominator. That's really what makes it tricky. Now, we'll deal with the fact that it's in the denominator at the very end. The first thing we need to do is to move the pieces that are added to the 1 over R2 to the other side, and we could do that just like we did with the by on the previous problem with subtraction. So we're going to subtract the 1 over R1 and the 1 over R3. So both of those are going to come to the other side. So I have 1 over R minus 1 over R1 minus 1 over R3. And there's nothing special about this particular order. These could be jumbled up as long as the sign's connected to the right to the right quantity. Now, what it would be really nice if we could do, it'd be really nice if we could just flip everything upside down. That'd be fabulous. Unfortunately, it would not give us the right value. It wouldn't work. So we would like to do something that looks a lot like cross multiplication. That would be nice, right, to try to get that R2 out of the denominator. But it's a little harder than that because the left-hand side is not a single fraction. So what we need to do then is get the left-hand side to be a single fraction, okay? So we're going to find the common denominator on the left-hand side. So let me get another color going here. We'll go with that. So this denominator on the left-hand side needs to include all three of the pieces that are already here, namely R, R1, and R3. So the first one has an R, but it doesn't have an R1 or an R3. The second one has I'm going to space this out just a little bit. The second one has an R1, but it doesn't have an R or an R3. The last one has an R3, but it doesn't have an R or an R1. So we're just making all the denominators the same by multiplying them by one another. I recognize the other side, 1 over R2, does not have a common denominator to that, but it's not really necessary at the moment. I'll show you why in a second. But for now, we're just working on the left-hand side. So on the left-hand side, I now have, and I'll write them in order. So it's R1, R3, minus R, R3, minus R, R1, and it's all over R, R1, R3. Okay, so I know it's messy, but is everybody good with where all the pieces came from at this point? So while it is true that I could do the cross multiplication, notice what would happen if I did that. I would multiply the R2 to everything right here, and then R2 would be a part of each of the individual pieces that are separated with subtractions, right? It would be in lots of places, which is not super helpful. What I can actually do is I can actually take the two fractions because they're equal, and I can flip them both upside down, which makes it better on this particular problem. Because the left-hand fraction has a 1 on top, so when I flip it upside down, the 1 on the bottom actually just disappears. So this is a true fact, and if you think about what fractions you know, if I had 1/2 and I had 2/4, and they're equal, right? If I flip them upside down, 2 over 1 and 4 over 2, they're also equal, yes? So this is a legit operation for fractions. I'm not cheating in any way, shape, or form, I promise. But I am shortcutting what I have to do. So I will flip this both upside down. So now I have R, R1, R3 on top. And I have the R1, R3 minus R, R3 minus R, R1 on bottom. And it equals R2. If you want to write down R2 over 1, which is equal to R2, just to remind yourself, that's fine. But I have solved this now for R2. So what are we doing? Well, we're doing symbol manipulation. That's what we're really doing in these three problems. Okay, we're doing symbol manipulation. So we're about to move into problem solving specifically, and we will be using, instead of symbol manipulation, we'll be using algebra manipulation, so we're usually using it more with numbers, not just letters that are involved. But the processes work the same. So our problem solving strategy, I just want to sort of run through this with you. I'm sure you have seen this before in different classes. They're not always written exactly the same way. Sometimes people combine certain steps, and I don't need you to show me every single step, but it's a good thing to keep in mind as you're working through a problem in case you get stuck especially. You need to read and understand the problem. What's it asking you for? What is it asking you to do? Number 2 says to draw a diagram if needed. Sometimes diagrams are helpful, especially if they're talking about something that is geometric, right? If we're looking at something that is a rectangle. I gave you a couple formulas for rectangles. A drawing might help. The third one says to decide on the variables that you need and write unknown quantities in terms of the variables. So what that means is that if you decide that you're going to let x be in the problem, you need to tell me what x is. X is or equals the number of students that went to the play. Okay, y is the number of parents that went to the play, or whatever it is. So whatever you're letting your x and your y, or your a and your b, or your l and your w, whatever they are, tell me what they are. Number 4 is to write an equation for the situation using a formula and or problem specifics. So the details from the problem will often push you toward a specific formula, and you're going to use that formula with your specific values evaluated in. Should solve the equation on step 5. That's what we've been doing on these last two with symbols. 6 and 7, 6 is actually really important and people don't always do. It says check your solution in the equation and in the problem context. Problem context is usually quite easy and often overlooked. So if you were finding, as my example before, the number of students that went to a play and you found out that it was 42.7, that should raise a red flag. I can't have 0.7 of a student, right? Probably should go back and make sure I didn't make some sort of an algebra or arithmetic error somewhere in my problems. Checking to make sure that it actually works in the equation is something different. That's actually plugging the number back in to see if it actually will work. But checking first for the context is usually pretty quick. And the 7th one is to make sure you answer the actual question being asked. And I know that may sound sort of obvious, but sometimes it's not, right? So like let's say, for instance, that we were working with perimeter, and at the very end we found out that the length equals 7, but the question asked me what was the perimeter. Well, I can find the perimeter based on the length, but I need to make sure what the question asked me to find, because it can sometimes ask a variety of things. So just making sure you're answering what is specifically asked. All right, so we're going to take a look at several different types of examples, hitting on a number of those different formulas that I gave you on that earlier slide. So our first example says if you borrow $100 and you pay back $105 at the end of 1 month, what was the simple interest rate? So, can you tell me, based on what you have seen before with your formulas that we've written down, which formula over here does it seem to sort of be beckoning you to use? The simple interest formula, right? I mean, and I know that looks sort of obvious right now because it's written simple interest, but on your test it's not going to have that, right? It's just going to say I equal PRT, and you're going to have to know that that means that's the simple interest formula. So yeah, it is I equal PRT. So our I equals P, R, and T. What is the unknown quantity in this particular situation? It's the rate. So R is our interest rate. So this is what I was talking about when I asked you to write down what your variable represents. It's the interest rate. I don't necessarily need to identify all the other pieces because I actually have numerical values that are substituting in for them. But for R, I don't. Right? That's what I'm looking for. So this is the correct formula. This is what our R represents. In this formula, the P represents the principal, how much money we borrow in this case. Or if you were the one who is lending money or putting money in the bank, P is the initial amount of whatever that quantity is. So what is P in our situation? Yeah, it's 100. The R I don't know. The I represents how much money you're getting or paying back after the fact. So that's my 105. Now, the T is very interesting because in this formula, T has to have a certain value. The T is always measured in years. So this isn't me identifying a variable per se, but as a reminder to you that the T is always measured in a yearly amount. So when they ask you something in this case about months, you have to take that into consideration. It says 1 month, but how much is 1 month of a year? 1/12. So my T in this equation is 1/2, or 1/12, excuse me. Because that's true on any interest formulas that we work with, and we're only working with simple interest right now. So we need to solve this, right? This is kind of like that area equals 1/2 base times height formula. I have a fractional piece, and I have a piece that's actually not fractional. It doesn't matter what order you deal with this in. I'm going to deal with the fractional piece first, just because it's on the end. I've got more space over there. And so how will I move the 1/12? Right. We'll multiply by the reciprocal, which is 12. Or you could say 12/1 if it feels more comfortable for you. Let me get out a calculator. If you have a calculator with you, I would encourage you to get one out as well. All right, so we need 12 times 105. That's 1260, 1,260, equals 100R, because of course these two cancel. Then what would I do? Divide by 100. And then there's one more. Oh, I made a mistake. Let me step back a second. I defined something wrong. This is what happened. I was like, that's not what my book says. I didn't write down what I was for you. I is the interest, not your new amount. There's another formula that I was thinking of. I apologize. The I value is not 105. It's just 5. So very sorry. It's the either the interest you've made or the interest you're paying on your amount. That's actually not 5 there either. 12 times 5, 60, right? There we go. We'll fix that. This is 0.6 now at this point. Okay, so is that okay? I'm sorry. All right, okay. This interest rate, much like time, has to be defined in a certain way. The R in the equation is a decimal value and not a percent value. So R is the interest rate as a decimal. So R percent is actually my percent. Over here, this 0.6 for R is correct, but the question asked me what is my percent. So I have to multiply by 100 in order to get the percent that this is. So this would be a 60% interest rate. Because the question itself asked for the annual interest rate, which is always given as a percentage. So kind of like, how do I know that the T is in years? Because this formula is set up to make the T be in years. This formula is set up so that the rate R is not a percent value in there. It's actually the decimal that corresponds to the percentage. So it is a 60% interest rate. The same thing happens with tax. I can't remember if I do an example of that one. I know you've got one in your... Yeah, I've got a simple interest one. It's quite the same way, but a little bit later. But the same thing happens with tax. So if you go to Walmart and you get the receipt at the end, it will tell you the percentage tax rate, right? So it'll tell you it's, like I was saying, we're going to pretend like it's 9.5%, but they're going to use 0.095, the interest, like the rate that is associated with it in decimal form, to figure out what your actual tax amount is going to be. So the same thing's happening here. So that's my answer to the question at the very end over here.
So what would it say if it's not asking?
It would never ask you for that. No. I mean, it might not ask you for the rate at all. It might ask you for how many months, right, or years or something like that. Or it might ask you for what do you actually owe at the end of the time. So you could use this formula right here that we were given at the original, and you could fill in other pieces. So like they could tell you that the interest rate was 4%. And that would mean that when you put the number in for R, you'd have to put in 0.04. That's the caveat that you'd have to remember from the other end. And that you'd have to remember that the I is actually the amount that you make or owe in interest added to your original amount to pay back. Yes?
So, like, so the interest is how much you borrowed, and then really, like, how much you paid back subtracted by how much you borrowed?
Yes, correct. It is. Yeah. So it is the same thing that happens it's the same thing that happens when you guys if you have a credit card and get a credit card statement that has a balance on it. Or if you get your loan amount, right? So if you have a car loan or maybe school loans someday that you're paying back, what will happen is that every month that you pay on the thing, you don't actually owe that much less on the car because there was an interest factor that it was just for the luxury of borrowing somebody's money that you had to take into effect. That's the $5 in this case. All right, let's do another one. This one's a little more direct. If the temperature at 11 p.m. on New Year's Eve in Times Square was 23 degrees Fahrenheit, what was the temperature in degrees Celsius? So, what equation am I using? Back there fast enough. Yeah, the temperature one. There's only one option right here, right? So I've got Celsius equals 5/9 Fahrenheit minus 32. And what is it that I'm actually looking for in this? This temperature in Celsius, right? So C is my temp in degrees Celsius. So I'm going to identify that that's the variable that I will still have once I start evaluating into this equation. So C is the unknown quantity. The 5/9 is already a number value. What is F? 23. This one's really nice and direct. 23 minus the 32. So again, keeping in mind order of operations on this one, since I have all numerical values on the right-hand side, I start from the inside and I work out. So I'll do 23 minus 32 first. You don't necessarily have to write this down, but just so that you know, I got -9. And when you multiply that by 5/9, hopefully you see the 9 canceling on that to give you a -5 degrees. So this is -5 degrees Celsius. Now think about that from what maybe you know about temperatures. If it's 23 degrees Fahrenheit outside, that's below freezing, right? Freezing is 32. That's why you're getting this negative inside here, right? And on a Celsius scale, freezing is the number 0. So the fact that I'm negative makes sense because I am below 0 as well. So that's that computational sort of perspective of the particular problem. Any questions on that one? Okay, the next one's going to involve a bit of a diagram. Julia's soybean field is 3 meters longer than it is wide. To increase her production, she plans to increase both the length and the width by 2 meters. If the new field is 46 meters square, larger than the old field, then what are the dimensions of the old field? So this just begs for a picture because it's talking about something that's got a geometric tone to it, right? It does. So we're going to start out by drawing a rectangle. And there's absolutely no reason for the rectangle to need to be perfect in the dimensions. We have no idea what they are anyway. It doesn't need to really look good. It just needs to have a rectangular sort of shape in your mind so that you can take into consideration the features that it's telling you. It says it's 3 meters longer than it is wide. So nowhere in here does it tell me how wide it is. So I'm going to call W the width of the original field. Because everything seems to be hinging upon that. Whoops, sorry about that. So it's 3 meters longer than it is wide. And then we're going to increase both the length and the width by 2. So it's hinging upon this original width. Now, not that you have to draw it this way in the sense that where I'm going to put my W, but usually we use the length as being the longer of the two sides. That's typical. So I'm going to put my W right here. And then my length says it's supposed to be 3 meters longer, which means it's W plus 3. Is that okay so far? Now I'm making my field bigger. Okay? So I need the same rectangle I already had before, but it's going to be longer and wider than it was before. So let me actually just draw a rectangle sort of superimposed on top of this that's a little bit longer and a little bit wider than it was before. Go with that. So this original length right here was W plus 3. And now it extends how much further out? 2 more. So instead of being W plus 3, it's now going to be W plus 5. So that's my new length of my field. Now my width right here was W, but now my width goes all the way up to here. What is my new width? W plus 2. Okay, is everybody good so far? Now it talks about the area of the new, of this increased piece, right? This piece, I'll shade it in yellow. It tells you the area of this piece is 46 meters squared, right? I don't necessarily have a direct equation to find the area of this missing little, bordering piece like this. But I do know the area formula for a couple of rectangles, and I do have 2 rectangles. So if I were to take this large rectangle, and I were to take off this smaller rectangle, right, subtract it off, I would have exactly the yellow piece that's trapped right here. Does that make sense? So if I just consider my 2 area formulas for the rectangles that I have, and I subtract them, I will get 46. So let's actually write down those 2 area formulas, much like I wrote down that this W is the width of the original field. So my area of my original field, the small one, what would the area equation be for my small field? W plus 3 times W, you're right. Length, W plus 3 times width, W. That's my original area. And then I have my new area. If you don't want to use original and new, you can use smaller and larger. It doesn't matter. Just identify that they are representing different quantities. The area of the newer or the larger field, that's the one that's in blue, right? My dimensions are written in blue. What's the area formula for that field? W plus 5 times W plus 2. And what we had mentioned before is that if I take my new field, the area, minus the original field's area, I should end up with 46. Okay, so do you have to write out every single one of these equations? No, you do not. You do need to write out for me that the W is the width of the original field. I need a definition of what W represents, especially because there's 2 widths that's being talked about here. Okay, so I really do need that. These other pieces might be able to, depending on how you think about it, be combined all into the next equation that we're about to write, depending on how easily you see the pieces coming about anyway. But if it helps you to write them all down the way I did, then by all means, please do so. I think I've got space. Yes, I do. So actually, let me do this. All right, so this is what I previously had. So you might be able to jump to the equation that I'm about to write, the area of the new field, which is W plus 5 times W plus 2, minus the area of the old or the smaller field, which was W plus 3 times W equals 46. We got to have that on there somewhere. And that's the equation we want to solve. It's got one variable, W. All of the formulas that we're going to work with are going to be linear as we work them out. Right now we're going to get a quadratic in the middle of this, but it will eventually work its way out. So we're going to multiply this out. So I have W squared plus 2W plus 5W plus 10. And then I have minus, I've got W squared, and again another minus 3W equals my 46. Should you see the squares canceling out? Yeah? Okay, so we're only working with solving linear equations, so they have to do that. Otherwise, you've got a mistake somewhere that you need to track down. Should not have any squareds at this point. Okay, they've got to collapse. I have 2 and 5, which makes 7 minus 3. So I have 4W plus 10 equals 46. That's where I am at this point. What's next? Subtract 10. So this is 4W equals 36. And then divide by 4. And W will equal 9. So this is one of those really classic cases where I need to go back and figure out what in the world I was asked to find, because there's a width, there's a length of the original one, there's a width and a length of the other one. There's areas that we talked about, and we could be asked any of those questions as we are looking at the particular question we started with. This one says, what are the dimensions of the old field? In other words, they want to know what is W plus 3 in W. Well, we found W. W is 9. So my dimensions are 9, and with units, it's 9 feet. We usually say length by width with the word by. If you don't put the word by, it's not a big deal, but 9 feet by. And what's the width, the length then? Yeah, it's W plus 3, so that would be 12. So it's 9 feet by 12 feet. Oh, was it meters? I'm so sorry. Thank you. Jumping back to my English metrics. Thank you. Meters, yes. 9 feet by 12 9 meters by 12 meters. I can't even say it right. Okay, any questions on that? Okay. Yeah.
Are they square?
They're not. That's a good question. So when we're measuring length of something, it's always linear units. It's area that gives us square units. So you can think about, like, when you're talking about area, you're talking about covering a surface, like the area of a room. But if you're talking about the length, you're talking about bordering something. And so we only have feet when we're talking about bordering, or meters, or whatever. Yes, right. So like if I multiplied these and I said, what is 9 times 12? I would get a quantity. And with my 9 times 12, that would be meters times meters, which would be meters squared. Yes. Okay, let's look at another one. Brent lent his brother Bob some money at 8% simple interest. He lent his sister Betty half as much at twice the interest rate. She must not be quite as reliable. That would be my guess. Both of the loans were for 1 year. If Brent made a total of $24 in interest, then how much did he lend to each one? So let's take a look. This is interest again, right? We did another interest problem. So the interest that we're talking about is I equal PRT. What we don't know in this case is the P. So we'll call it, in fact, since they're both letters of B, so we'll call it P1 is the loan amount, and we'll just go in order. Bob was first, right? Loan amount to Bob. And then we'll call P2 the loan amount to Betty. He did not loan them the same amount, so I can't use just P to represent that because they are different values. So let's actually create an equation for each of the two siblings. We have Bob and we have Betty. And what does it say that we know about each of them? Well, we know a relationship between how much he loaned each of them, right? That's important. So if Bob is P1, then Betty is actually going to be the P2, and we will actually piece in something with that in a moment about the fact that he loaned her half as much. The other thing that it tells us is the rates, but it doesn't actually, it does give us, it says it's 8% simple interest for Bob. So this one kind of goes back, Elizabeth, to what you were asking before about the rates. So we're always going to take that 8% and write it as a decimal, 0.08. But what was the interest rate? Oops, I'm sorry, I put that in Betty's spot. What was the interest rate for Betty? What does it say? Twice that. So what would twice that be? 0.16, yeah. 16% is 0.16. And then it also tells us the time. How long is the time? 1 year. One's a wonderful value because it doesn't change things, right, when we multiply. So here's our value. It might be good for us to also write down that this is the first interest, interest 1, and this is our second interest, interest 2, because there's no reason they would have to actually give him the same amount of interest in general. Let me see if I have space on the next slide like I did on the last one. I do. All right. Now, a couple more things as we go back. It tells us there's a relationship, like we said, between the principal. The principal for Bob, let me say the principal for Betty. The principal of Betty's is half of the principal that he lent to Bob, right? So if Bob's principal is P1, then what would her P2 actually be? Yeah, P1 divided by 2 or times 1/2. And you can use decimals if you want. So if you want to put 0.5 P2, that's fine, or P1, that's fine. I'm going to write it as divided by 2 times 0.16. So there's my first interest, and here's my second interest. And then it says when I add these interests together, namely when I add together this and this, Brent, the brother that loaned the money, makes a certain amount of money. How much money does he make? That was the $24. So this is the actual equation I have. It's P1 times 0.08 plus P1 over 2, or 1/2 of it, times 0.16, and it has to equal the $24 that he makes overall. Now, this is actually quite lovely in this particular situation. He could have loaned him a third or something like that. It doesn't have to be this nice, wonderful ratio, but it is beautiful because when we have this 2 right here and this 0.16 right here, those are going to cancel in very much the same way and give me that same 0.8 here, 0.08 here. So I actually am going to have P1 times 0.08, and these two canceling are going to give me another P1 times 0.08. There's no reason that would have had to be the case. It just happened out this way, okay? We could have doubled the interest rate and a third of the value that they gave him or something, and that wouldn't happen. But it does happen here. So I have 0.08p, and I have another 0.08p. Those would add to 0.16 P1. Is that okay? And then what would I do with my 0.16? Yep, I would divide. So I have P1 is actually 150. So that's the solving of all my equations that I created. Let's go back and ask the question, read the question that we were asked. How much did he lend to each sibling? So P1 is how much he lent. Who? That's Bob. So Bob received 150, and we want the units on there, so dollars. What did Betty receive? 75. How'd you get 75? Yeah, she got half. That's the description we had. So we would divide by 2 to get 75. Any questions on that one? Yep.
Like, I don't understand when we have like P1 with 0.08 and plus, why is it not P2 over 2?
P2 represented the amount that Betty had, and P2 was 1/2 of P1 because it said that Betty had half as much, twice the interest, but had half as much is really the kicker. The half as much as Bob, and so Bob had P1, so she had P1 divided by 2. Yep. Any other questions on that one? Okay, we have a couple left. This is a very classic example of work. So Rita can process a batch of insurance claims in 4 hours working alone. Eduardo can process a batch of insurance claims in 2 hours working alone. How long would it take them to process a batch of claims if they work together? Now, it's really important for you to realize that the answer is not 3 hours. Because that's sort of like our gut reaction is like, we're just going to do the average. And that doesn't make any sense because Eduardo is faster than that all by himself, right? So whatever our answer is, it has to be lower than 2. Does that make sense to everyone? Right? Because he can do it in 2 hours, and now they're working together, so it should be faster than his time. So work is what's going on here, right? So another one you'll see sometimes that shows up is they'll talk about people mowing lawns. Joe can mow the lawn in this amount of time, and Jill can mow the lawn in this amount of time. What if they do it together? Or making whatever. But you're always doing some kind of work. So our work formula from the previous slides is actually work equals rate times time. That's your basic formula, okay? So we're going to create, much like we did over here with our interest for Bob and Betty, we're going to create 2 separate statements about what happens for each of them individually, and then we're going to combine them to see what happens overall. So we have, what's our first one? Rita. So for Rita, it takes her 4 hours, right? So if it takes her 4 hours to complete the job, how much would she complete in 1 hour? 1/4 of the job. That's her rate. Her rate is 1/4 of the job. You can think of it as how much per hour, right? She's working at a rate of 1/4 per hour. And she works for a certain length of time. She works for 4 hours when she does the job by herself, but when she's doing the job with the other person, she will work for fewer amounts of hours, right? It will be fewer than 4 hours. We have the same situation for Eduardo. So for Eduardo, he has work he does, but he works at a faster rate. His rate is not 1/4 of the job per hour. His rate is 1/2 of the job per hour. And again, he's going to work for a certain length of time, 2 hours if he were working alone, less if he's working with Rita. Okay, so these are their individual rates of work. Okay, so if they work for 1 hour, this one gets done with 1/4 of the job, this one gets done with 1/2 of the job. The answer's got to be more than 1 and less than 2, doesn't it? Yeah, because if I put the number 1 in, 1/4 plus 1/2 is not quite the whole job done. So what we're actually trying to do is we're trying to figure out how we get the whole job done. Let me actually copy this to the next slide like I've been doing to create our combination statement. So as I'm looking for the whole job, I need Rita working. She's working at 1/4 T. I need Eduardo working. He's working at 1/2 T. And I want them to keep working until the whole job is done. So the one on the other side, this is representing 100% of the job done. Much like the 1/4 is representing 1/4 of the job done and 1/2 is representing 1/2 of the job done. Does that make sense to everybody? So when I said a moment ago, if I just plug the number 1 in, that's not enough. This is what I'm talking about. If they each worked for 1 hour, we would not have the full 100% of the job done. I'd have 3/4 of it done. But if we work for 2 hours, we're overcompensating because Eduardo could have done that by himself already. So we're going to solve this problem using fractions. So we'll get a common denominator, right? It's a nice, easy one on this one. So I have 1/4, or actually I'm just going to put T over 4, plus 2T over 4 equals 1. So 1T plus 2T is 3T over 4 equals 1. So what will I do to get rid of the 3 and the 4? Okay, we can multiply by 4. If you want to do it all in one time, you can. We can do it in 2 steps as well. So if I multiply by 4, I'm left with 3T on the left and now 4 on the right. And then divide by 3. And while it's not a very pretty number, this is 4/3 of an hour. Or if it helps you to think about it, it's 1 1/3 of an hour. Or again, really what this means is it's 1 hour and 20 minutes. I'm not asking you to actually write all that out, but it does make sense to talk about 1/3 of an hour. It's 20 minutes. So up here, when we multiplied by 4, then divided by 3, you could also multiply by 4/3 right here if you wish to do it directly instead of doing it in 2 steps. Let's actually double check the question that was asked because I zoomed past it. It just actually says, how long will it take to process the batch of claims together? So T is the combined time. I failed to write that down, but that is how I was using the T. And that means that my T at the end, being 4/3 of an hour, or 1 1/3 hour, or 1 hour and 20 minutes, any of those are perfectly fine answers to the question being asked. Any questions on that one? Okay. The last question is a real, it's kind of a confusing one to read because the word orange shows up so many times. So let me show you. A beverage producer makes 2 products, orange drink containing 10% orange juice and orange delight containing 50% orange juice. Lots of the word orange, right? How many gallons of orange delight must be mixed with 300 gallons of orange drink to create a new product, Orange Delicious, containing 40% orange juice? Okay? So an analog to this problem that you sometimes see in books is they'll talk about mixing nuts. I don't know why we would always want to mix nuts, but we do. So you have this nut mixture and you have this nut mixture, and you're trying to combine them to have a nut mixture that costs somewhere in between that amount of cost. So these things are often mixing something together. This one's mixing different amounts of orange products. So as I'm working through this, I'm probably not going to keep writing the word orange because there's just no need. Everything has the word orange in it. And this one actually works really, really nicely to set up some sort of a table to organize the information because there's a lot of information going on. So as we take a look at this, we have 2 different things that we're mixing. We're mixing orange drink and we're mixing orange delight. I mean, those are the 2 different kinds of things. And they each contain a different amount of orange juice in them. So there is a percentage of orange juice, I'll just do percent OJ, in each of these products. So let's actually fill that in first. So if you look back over here, what is the percentage of orange juice in orange drink? It's 10%. So for right now, I'm just going to write 10% in my table. What is the percent of orange juice in Orange Delight? 50%. Oh, there's one more. Sorry, I left it off. Orangelicious. That's the one we're trying to create, isn't it? So it's just going to say alicious. What do we want our Orangelicious percentage to be? Yeah, it's 40%. Now there's different quantities of this being mixed together. So the next column I'm going to put here is going to be the gallons that are going into it. So how many gallons do I have of orange drink? Delight, sorry, which was the first one? Orange drink was my first one. 300 gallons of orange drink. Whoops, sorry. How many gallons do I have of Orange Delight? You don't know. So that's going to be the thing I don't know. Use whatever letter you wish. I'll just use X. So over here, my X is actually my gallons of Orange Delight. So then, how many gallons am I going to have of Orangelicious? You're right, X plus 300. This is way too large. X plus 300. Yeah, it's X plus 300. And then the last quantity over here is we're going to represent how many gallons of orange juice it takes to make that product. So if you take a look at those percentages, if I have 300 gallons of orange drink and 10% of it is an orange juice, it's not 300 gallons of orange juice, right? A part of the orange drink is orange juice and a part of it is something else. Maybe it's seltzer, maybe it's lemon flavor, maybe it's water, we don't know, but it's something else. But a certain amount of that came from orange juice. In particular, if you take these two quantities and you multiply them together, that will tell you how much orange juice you had. But the 10%, much like on our earlier problems where we've had percent, is the decimal 0.10. This is the decimal 0.5 or 0.50, and this is the decimal 0.4 or 0.40. Right? That's the decimal associated. So if I have 300 gallons and it's 10% orange juice, 30 gallons of that 300 came from an orange juice quantity. On the second one, I don't know exactly what it is, but I know it's 0.5x, whatever the x number of gallons is. And the last one, quite similarly, I don't know what it is, but it's 0.4 of whatever the x plus 300 is. Okay, is everybody okay so far? We're trying to figure out how much of each of the things are in our product. So what we're going for here then at the end, it said, is that it wanted us to find out how many gallons of Orange Delight must be mixed with the 300 gallons of orange drink to create the product Orangelicious containing 40% juice. So I want these two right here to actually add up to equal this right here. That's physically what I'm doing. I'm mixing orange drink and I'm mixing Orange Delight and I'm creating Orangelicious by doing so. So over here I have 30 plus the 0.5x. That's the two individual, the drink and the delight. That's their orange juice quantity that they have in there. And it's going to equal the 0.4 times the x plus 300. That's the amount of orange juice. So this is the amount of orange juice in orange drink. This is the amount of orange juice in Orange Delight. And this is the amount of orange juice that is going into, or the percentage rather, that's going into my, what's the last one? Orangelicious. So this is the equation that we're going to be solving. So we have 30 plus 0.5x. As we distribute this one through, I have 0.4x plus 120. Here. So what would I do next to solve? Okay, we could subtract the 30, sure. So now I have 0.5x on the left, I still have the 0.4x on the right, and now I have 90 on the right as well. Now what? Subtract the 0.4. I need to move the x's on the same side. So that leaves me with 90 on the right. 0.5x minus 0.4x is 0.1x. And then what? Divide by 0.1. And what is 90 divided by 0.1? It is 900. Now x, up in the right-hand corner here, represented the gallons of Orange Delight. So this right here is gallons of Orange Delight. And we want to make sure, or we want to double check, whether that's actually what we're asked to find or something slightly different. So the question, sorry, I meant to flip back here, asked us, how many gallons of Orange Delight must be mixed? So that is what our x actually was and what we found, right? So this answered the question that I was being asked. 900 gallons of Orange Delight. So going back and thinking about your problem, what you're saying is that you'd need 300 gallons of orange drink mixed with 900 gallons of Orange Delight. And if I mixed those, I'll end up with 1,200 gallons combined, right? And it will have the appropriate 40% ratio of orange juice inside of the product. All right, so this homework, just one assignment, but it is a challenging one because it's all word problems, or at least mostly so, will be due on Thursday.